Hello, everyone. Welcome to Stat 310, Lecture 13. So I presume you're listening to this after taking the first midterm. Now we're kind of going to move on to a new topic. So the first sort of the first midterm, we focused on chapters 6, 7, and 8, where we developed some basic tools, and in particular in chapter 8, we discussed topics of like parameter estimation and developing confidence intervals around that. And that's going to, the calculations and methods that we learned in that chapter are going to really serve us well for the remainder of the course and also this chapter here. So chapter 9 moves on to a different topic, which is related to hypothesis testing, which is also a very important topic. I'd say sort of the chapters 8 and 9 are really sort of the two most fundamental topics from a point of view of like developing statistical frameworks and theories. And so the next 4 to 5 lectures is really going to focus on chapter 9, which is on hypothesis testing. Today for lecture 13, we're going to first just introduce some of the basics. So it'll largely focus on the material from sections 9.1 and 9.2 of the textbook. So in particular, things like the null and alternative hypothesis, concepts of size and power, which we'll define before the end of today's lecture or the end of this lecture. So just to provide a background and motivation for why we're covering hypothesis testing. So in statistics, our goal is often to make data-driven decisions or predictions, and these are typically like binary, like yes, no types of decisions or predictions. So just to give you a few examples, so will the Republicans or Democrats win the upcoming election? That's kind of a yes, no decision. Will there be a vaccine for COVID-19 by the end of 2020 or some other future date? That's another kind of yes, no question. Another question associated with Wisconsin: Will the Packers make the playoffs this year? That's another yes no question that we'd ideally like to kind of use some data driven approaches to try to answer that. And so because these are yes no questions, what we learned in chapter 8 with like parameter estimates and confidence intervals, they're certainly very useful, but they don't quite if someone asks you for a yes or no answer to these questions, or at least a prediction, it doesn't really nothing that we learned in chapter 8 really kind of allowed us to do that. And so hypothesis testing, which is what we're learning about in chapter 9, allows us to develop such a framework. So we're going to kind of ask we're going to be able to answer kind of yes no questions or put it in a hypothesis testing framework that we're going to discuss starting today that allows us to answer these kinds of questions. And actually, so from a calculations perspective, many of the existing methods that we learned, like maximum likelihood, calculating confidence intervals in maximum likelihood, and so on, are going to actually be very applicable. So from a calculations and a math perspective, there's not many new mathematical techniques we're going to learn in this chapter. The main challenge is actually just going to be understanding the testing frameworks that we develop. So understanding kind of what exactly the concepts mean. And so that allows us to kind of determine how to use the various calculations that we've learned in chapter 8. So that's really going to be the main focus of chapter 9. And like I like to do at the beginning of topics, I'm going to discuss sort of how chapter 9 fits into a statistical framework. So our general statistical framework. So we have our typical data is from some sample x1 through to xn. We typically have a model. We assume kind of independent draws from some distribution. So it might be like normal or Bernoulli or any other distribution we might think about. And then we often, with the distribution, have a parameter of interest. And that's going to be the case in this chapter as well. We're going to have a parameter of interest. So it might be, for example, the probability that someone will vote Democrats, or the probability of there being a vaccine before a certain time t, or the waiting time until a vaccine comes out. So this might be kind of the parameter of interest that we don't know, that we're trying to kind of infer from the data. The third component is the statistics / estimator, and this is what we're going to refer to. So in chapter 9, this is going to be like a test statistic. So it's not going to be like necessarily too different from what we've seen in our statistics in like up till now. Like we've seen things like the sample mean or the maximum likelihood estimator or the method of moments estimator, and some of those will come up here. But we're going to also potentially learn other statistics that are essentially just functions of the data that are going to help us in our hypothesis testing framework. And then the next thing is, obviously the distribution of the statistics, because that's going to allow us to do our calculations. And we've, seen this in chapter 8 as well when we're trying to develop confidence intervals. And in this case, this is going to be under a certain hypothesis, and we're going to be more specific about what that actually is. So this is where we're going to, the note, like where testing is going to be a little bit different from what we learned in chapter 8 on estimation, because we're going to talk about distributions kind of under a certain hypothesis. And where there's probably going to be the most work in this chapter is like the analysis. So what yes, no, decision So what yes, no decision do we conclude from the data? And, as the other thing to keep in mind is, this is going to depend on how we construct our hypothesis tests. And the point of today's lecture is to kind of be more concrete about these vague statements. So obviously there's, you have a lot of choices in terms of how to construct tests. And we're going to kind of try to develop a general framework that allows you to construct hypothesis tests and allows you to make these decisions. But as with everything in statistics, you have certain choices that we'll see shortly. So what I'm going to do is I'm going to introduce the basic testing framework and components of our hypothesis testing framework, and I'm going to also try to sort of give some intuition behind these various concepts. And I think the easiest way to give intuition is to kind of have an example in the background that we can always relate it back to, because that kind of makes these definitions a little bit concrete. So I'm going to go back to an example we've kind of already seen, which is, voting. And we're going to look at the question, will Republicans win the 2020 election? Okay, so that's kind of the yes-no question that we're asking that we want an answer to. And you might imagine that our data is we sample 100 people, and we'll say that 55 out of 100 vote Republican. And again, I'm kind of assuming that I'm assuming that that everyone votes either Republican or Democrat. So that obviously is a very strong simplifying assumption, but we're going to assume that for the data that we have here. Okay, so now let's look at the kind of the components of the testing framework. So the first sort of key component is what's called the null hypothesis. Okay, I guess I'll put this as 1A because we're going to have a different kind of hypothesis as well that we're testing against. So what that basically is that so this can be thought of as like a baseline hypothesis. And I'm going to use this notation, so H naught for the null hypothesis. And that might be, for example, theta equals theta naught, for example. So theta is the parameter of interest. And, H naught says that fix theta equal to theta 0. So just to relate that back to the example, you might assume that the theta is the probability. Let me see. Probability of voting Republican. Republican. And so, you might set that the null, H naught, is that theta equals 0.5, that it's a 50-50 chance. So like, this is very important because like, obviously how you set the null hypothesis is going to determine your conclusion. So all of the components that I define here are going to determine like how you like determine what conclusion you make at the end. So how you choose that is certainly going to influence it. But in this particular case, for example, choosing theta equals 0.5 seems a reasonable enough kind of an assessment because without any prior knowledge, you might expect that there's no like sort of leaning one way or the other. But let's just that's what we might kind of assume for this null hypothesis. So that's the first component, is the null hypothesis. The second component is the alternative hypothesis. And so I'm going to use this notation H1. And this could be, there are several, you could have that the alternative is just theta not equal to theta 0, which is kind of the opposite of the null, or, theta bigger than theta 0 or theta less than theta 0. And so that's kind of saying like, you're trying to say something that isn't, it's, the null hypothesis does not occur, or the, a better way to think about it is sort of not part of the null hypothesis. Okay. So for example, in the voting example, because you're asking the question whether the Republicans, we know that theta is the probability of voting Republican. and that's if you take a random person from the population, then you might have that your alternative hypothesis is theta bigger than 0.5. Okay, and that's a perfectly valid alternative hypothesis. In this case, it kind of makes sense because you're looking at whether Republicans win the election. Yes, no answer to that. You could ask it and the alternative question of whether the Democrats would win, and then a more appropriate alternative hypothesis might be that theta less than 0.5, because that's kind of like you're trying to answer yes if theta is less than 0.5. So the way to just interpret this is that the interpretation is that null is like the null hypothesis is a baseline belief. Okay. And the key question that you're really trying to answer is like, does your data provide enough evidence to reject the null hypothesis? So there's going to be two outcomes. One is that you reject the null hypothesis, which would or the other option is obviously that you accept the null hypothesis. Okay, and so that's that's essentially what we're going to try to do to determine a framework that allows us to either reject the null or accept the null. So in that case, that's either going to say that if we rejected the null hypothesis in this case, then we'd say that the Republicans have evidence to believe that the Republicans will win the election based on the data that we have. And then if we accept the null hypothesis, that's not really saying that we're accepting that the Republicans won't win, I'd say. It's more saying that we don't have enough evidence from the data that we see to reject the null. Okay, so always bear in mind that the null hypothesis is kind of in the driver's seat because it is the null hypothesis, that you need to find evidence to reject the null hypothesis. It's not that the null always kind of has the advantage in that sense, because you're accepting that it's true until you find evidence that you can reject it. Okay, so the next kind of key component is the test statistic. So this is going to be a function of our data, like x1, x2 up to xn. So we can call that maybe like t of x1, x2 up to xn. So for example, if your data is, in our voting example, xi is just 1 if person votes Republican, and 0 otherwise, then we know then one perfectly reasonable test statistic you could think about is this sample mean. Okay, and so this is the proportion of people in the sample who vote Republican. Okay, so so this is this kind of provides us the the distribution. This kind of provides it's the test statistic, which is again kind of that third component of our framework. And so in our example, it would just be 55 out of 100 or 0.55. So we've got a value that's 0.55 is our as the proportion of people who vote Republican. And I guess the question we'd like to ask is, if we had, is that enough evidence to say that we're going to reject the null of, theta equals 0.5, which is, that the Republicans would not win with that, with an even number. Okay, and then third component, so the third component, which is again kind of related to the fourth component of our original statistical framework, is the distribution of the test statistic, but under the null hypothesis. So remember that theta is unknown, and so the H naught, for example, might be theta belongs to some set, say we'll call that S0. So for example, if that set is just 1 point, we just have theta equals theta 0. Okay, and so so in the voting example, we have H naught is theta equals 0.5. And so we could say, our test statistic is X bar, Xi. And so we know that Xi, so, a perfectly reasonable assumption would be that Xi is going to be Bernoulli theta. So under H naught, Xi would be Bernoulli 0.5. And then so X bar, we are typically going to end up using the normal approximation for these. And so we're going to again use the normal approximation here. So it's going to be approximately normal. And then the mean, as we know, is theta or 0.5. And the variance is sigma squared over n, which is going to be, theta times 1 minus theta over n, which is, here we have theta equals 0.5 and n equals 100. So that would be X bar would approximately be distributed as normal with a mean of 0.5 and a variance of 1 over 400. Okay, so so this is the distribution, and note that this assumes theta equals 0.5, and this is kind of the assumption of the null hypothesis. This is the assumption of the null hypothesis. Okay, and this leads to another just couple of definitions that are that are useful. So a hypothesis, this could be H0 or H1, is simple if you can determine the distribution of the test statistic from otherwise it is composite. Okay, so this kind of definition sounds a little bit obscure, but all it's really saying is that if you know the if you're given the null hypothesis, can you determine the distribution of your test statistics? So, and if we see some examples, this will hopefully be pretty clear. So, if we look at, for example, like theta equals theta 0, this is usually simple since H naught, or we'll say H naught, contains only single value of theta. And so and so that's why it's a simple hypothesis, because once you know your theta, you know the distribution of your xi's, which in turn means you know your distribution of the t, the test statistic t. On the other hand, if we look at the H1 here, which might be theta bigger than theta 0, that's usually composite. Composite since H1 has more than one value of theta in it. Okay, and so this is, you know, again, if you think about this intuitively, it hopefully makes a little bit of sense, because, you know, if you're saying theta is bigger than 0.5, is it 0.6, is it 0.7, is it 0.55? And so you don't actually know what the theta value is, and because you don't know the theta value, you can't really determine the distribution of the statistic, because it's going to be different depending on the value of theta. So, you know, in composite hypotheses, distribution of the test statistic usually unknown, since there are more than one value of theta. Okay. And you know, you'll get more comfortable with this notation and these ideas shortly. So far we have kind of the null and alternative hypotheses, and then our test statistic and our distribution of our test statistic. And so these are hopefully not overly new, like the distributions are something we've already seen. But the next kind of key component is really the thing that drives, you know, how big or small your test statistic needs to be, which is referred to as a significance level or size of the test. Okay, it has a lot of different terms. We're going to use this notation alpha. And that's basically, the definition is the probability that you reject H naught given that H naught is true. So this is also referred to sometimes as the type 1 error. Because obviously if H naught is true, you typically want to you typically want to make sure that you would actually accept H naught or not reject it. So this is why it's referred to as an error, because if you reject H naught when H naught is true, that's telling you that you've made an error. So you want alpha to be as small as possible. But obviously you can't have alpha being equal to 0 because you have randomness in your data. So if you set alpha to 0, then you'll just never ever reject your test, I guess. And that's sort of not that's not, you don't want something where you never ever reject your test. And so alpha is usually chosen a priori. So it's usually you usually design a test so that your alpha is a specific value, and then that's often something like 0.05. So like the chance of you rejecting H naught is like 5%, and so this is like typically the last thing that you need to know before designing your test. And so once you set that alpha, this will lead to the acceptance and rejection regions. Okay, so alpha equals probability that you reject H naught given H naught is true. Okay, and then you have your test statistic, T of x1, x2 up to xn. So clearly your test statistic is like what's like determined by your data. And so whatever value that, whether your data lies in, like your statistic lies in a particular region or not, is going to determine whether you accept or reject your test. So we're going to say the rejection region we'll call that the set R is equal to so S is or no, let me just use R, sorry. So R, which is I know that's, so we'll just say the script R, which is a subset of say the, that's bad notation. Let me just go back to S. Sorry about that. We're gonna say S is, which is a subset of the real line, such that T of x1, x2 up to xn is in S, and so so you reject if T of x1, x2 up to xn is in S, and the acceptance region is it's another subset of R where like there's no intersection with like, so the so we have no intersection hopefully between the acceptance and rejection regions, and you're gonna accept, so you're gonna reject H naught and you're gonna accept H naught if T of x1, xn is in A. Okay, so there's a lot of notation in that, but let's kind of go through the example to see what those rejection and acceptance regions might be. So remember that we have our, so this is our voting example. So we're going to kind of start to put things together and say that H naught is theta equals 0.5. And H alternative is theta bigger than 0.5. So remember that theta is probability you vote Republican. Okay, and so I'll call this sort of component 1. Component 2, we have our test statistic. The test statistic, which is x bar, which is 1 over n. Okay, and the actual value is here you have n equals 100 and x bar is 0.55. And then the third component is distribution of test statistic under H naught. So under H naught, we know that xi is distributed Bernoulli 0.5, and we know that x bar has the approximate distribution of normal with mean 0.5 and variance 1 over 400. Okay, and so now let's move on to the size or significance level. Okay, and so this is probably the thing where you need to maybe concentrate most on how we kind of determine these significance levels. So the probability that you reject H naught given H naught is true. And so that's your alpha. And we're gonna set alpha equals 0.05. So just remember that this is something we set. This is not something that like you can determine from the data. This is something that you preset, and that's going to determine your acceptance regions. Reject H naught, and then this is going to be given theta is 0.5 because that's our null hypothesis. And then remember that we reject H naught if our test statistic T of x1, x2 up to xn lies in some set S, right? So that's going to be, the probability that x bar lies in some set S given that theta equals 0.5. And then the key question is, what is S? Okay. And so this is where you need to carefully think about what your alternative hypothesis is. So alternative hypothesis is like theta bigger than 0.5 here, right? So because that's our alternative hypothesis, it makes sense to reject H naught if X bar is bigger than C for some C. So if you think about this intuitively, if you're counting the proportion of people who are voting Republican, the greater that is, the more likely you are to reject the null hypothesis that theta is 0.5. And so so your S here, another way to think about it is S goes from C to infinity. But like you want to, So you have probability x bar is bigger than c given theta equals 0.5. And you know that x bar has the distribution, approximate distribution, normal of mean 0.5 and variance of 1 over 400. Okay. Under null, under h naught. Okay, so because this is our distribution, we've set alpha equal to 0.05. So that's, we know that probability x bar bigger than c is given theta equals 0.5 is 0.05. And so the question is, what is c? And this determines rejection and acceptance regions. Okay. So this is where we use what we already know about kind of normal distributions and normal tables. So since x bar has this normal distribution with mean of 0.5 and 1 over 400, then we typically do what we do, which is to standardize, which is that then we have that 20 times x bar minus 0.5 is normal 0, 1. So we have that probability x bar bigger than c given theta equals 0.5 equals probability that 20 x bar minus 0.5 is bigger than 20 times c. And that should equal to 0.05. That's just the probability that z is bigger than 20 times c. Okay. Okay, and so this is where we use the normal table to, the probability that we want to calculate here is this, so this needs to be 0.05, this tail probability, and I believe if you look this up on a normal table, you should get about 1.64 here. Okay, so we have therefore that 20 times c minus 0.5 should equal to 1.64, right? So what that means is that the threshold we have is that c is equal to 0.5 plus 1.64 over 20. And so that should give you c is 0.582. Okay, so what that means is that our to have a test with alpha equals 0.05, we would reject null if x bar is bigger than 0.582, and this is also known as the this would be our rejection region. And then we'd accept, I prefer to say not reject, to be honest, because if x bar is less than or equal to 0.582. Okay. And so and the reason I prefer to say not reject, because remember that as I said right at the beginning of this, that the null hypothesis is kind of in the driver's seat because we need to find data evidence to reject the null, which means that even if you seem to have some evidence of rejecting the null, it just may not be enough. So if we actually go back to our data, so in our sample, x bar equals 0.55. If x bar equals 0.55, therefore we would accept or not reject null. And this is where I think this is why the point about the null hypothesis is really important. Because in our sample data, I mean, 55 out of 100 people still voted Republican. So that would sort of suggest to you that, if you had to make a decision one way or the other, that you would sort of possibly predict that the Republicans would win based on that sample. But our null hypothesis is kind of in the driver's seat, that theta equals 0.5. So because you only had a sample of 100, the 0.55 was not large enough. You needed that to be 0.59 or more at the significance level of like at the significance level of 0.05. So another way to think about it is if you maybe change that alpha to something different, say like maybe 0.2 rather than 0.05, I would guess you would probably then reject null. So you would actually potentially reject it if you made your alpha bigger, if you allowed more errors or more type 1 errors. But if we set it to 0.05, you wouldn't have enough. You don't have enough evidence to reject. So this, I just want to say this again. This does not mean H naught is true. It only means we did not have enough evidence to reject H naught. And that's a really important distinction. We're not, like, by accepting H naught or by not rejecting H naught, we're not claiming that that's true. We're just saying we don't have enough evidence. So for example, in this voting case, you might say, well, okay, because we only had a sample size of 100, that was not enough evidence. So let's maybe get a sample of 1,000. And if you got a sample of 1,000, you're more likely to have enough evidence to reject if that if that sample was kind of as biased towards Republicans as this. So if we just kind of looked at, so let's take the example where instead you in a sample of 1,000, 550 vote Republican. So I'm claiming that in this case, you should reject H0 at alpha equals 0.05 level. And I'm leaving that for you as exercises to go through the testing framework to validate this. Okay, so this is something I'm going to leave for you because I think it's a good exercise for you to go through the whole testing framework that we've kind of discussed and developed here to check this. So this is actually going to give, like, the calculations are going to be almost identical. The only thing that's changed here is the sample size n, and that'll actually change your critical threshold. So, that critical threshold C, which was 0.582, that's going to be a lot closer to 0.5 when you make n equals to 1,000. And so that's going to kind of allow you to potentially reject the null hypothesis if you have more data. So that's something to kind of to keep in mind and to try to sort of work on before moving on to the next lecture. And that'll also, I think, kind of put in place some basic, that'll hopefully pin down the basics in terms of the understanding of this framework. Another thing that I wanted to talk about as a set of basics is the notion of power of the test. And so this is kind of, in some sense, this is in contrast to size. So typically you want your size to be as small as possible, but the price you pay is you also want to be able to, this is the probability that you reject H0 given that H1 is true, given that the alternative is true. So I'm going to call this 1 minus beta. So beta here, that's sort of the equivalent of the probability that you'll accept H0 given that H1 is true. So this is often referred to as type 2 error, because if H1 is true, you would actually want to reject the null hypothesis, but you're actually going to accept it. So that's that's referred to as the power of the test. And so so 1 minus beta is the power, so beta is the type 2 error. So typically you want beta to be small. And that means that 1 minus beta is large. Okay, so we have this notion of the size or significance level alpha, which is alpha, and typically what we do is we set alpha to determine acceptance and rejection regions. And then we have the power, and that we denote as 1 minus beta. And so the idea here is that we want power 1 minus beta as large as possible. Okay, and so so this is typically this is something we can actually calculate if the H1 is simple. If the alternative hypothesis is simple. Okay, so the size is something that you actually set. You kind of predefine the size alpha, and the power, which is 1 minus beta. So you want beta to be small and you want 1 minus beta to be large. This is something we can calculate if H1 is simple. So to take a concrete example again, if you're if we go back to the voting example, once again, the reason why we need H1 to be simple is that a simple hypothesis means you can determine the distribution of the test statistic given that hypothesis is true. So here you've got H0 is theta equals 0.5, and then we have that our rejection, and then you set alpha equal to 0.05, and then we therefore have rejection region is going to be x bar bigger than 0.582. So this is something we've already calculated. And then the question is if h1 is say theta equals 0.6, which is a simple hypothesis, then find power of the test. Okay, so this is the probability that you reject h1 or reject h0 given that h1 is true. Okay, and so this is going to be so this is the probability that x bar is bigger than 0.582 given that theta now is 0.6. So this is something that we haven't really seen before that's a bit different, that we're actually going to get a different distribution depending on which hypothesis we use. So if we use the alternative hypothesis, we're setting theta equals 0.6, which was different to what we got from the null. So under h1, the distribution of x bar now changes. So x bar is going to be now approximately normal, but the mean is going to change to 0.6. The variance is going to be so it's going to be theta times, so it's going to be 100 again, and then 0.4 times 0.6, because now that's kind of our new theta, and this is our 1 minus theta, and this is our n. Okay, and so therefore, if we wanted to calculate the probability that x bar is bigger than 0.582, given theta equals 0.6. So if you, again, kind of do the standard normal types of things that we do, this is going to be 10 times the square root of, or 10 divided by the square root of 0.24 times x bar minus 0.6 is going to be normal 0.1 under h1. And so what that means is, therefore, the probability that x bar is bigger than 0.582, that's going to be, or given theta equals 0.6, that's going to be probability okay, and so if we, again, this is a z score, and so this is gonna be about 20 times negative 0.018. And so we're going to get that this is z bigger than negative 0.36. Okay, so this is okay, and so if we look that up, I actually don't have the table in front of me right now, but I believe you're going to get approximately 0.6 if you do that, but I'll correct that in the next lecture. Okay, so and then the other thing to point out is if h1 is composite. So we saw that example, if we had theta bigger than 0.5, you can get a power curve where you get a different power for each choice of theta in H1. So I've done it for theta equals 0.6. But if you imagine that if the bigger that you make, in some sense, like the bigger that you make your theta, the less, or your alternative value. So if your theta was equal to say 0.7 instead, you would get kind of a larger power. So so you can think about it as, if you set theta equals 0.5 here, you'd actually just get exactly 0.05 because you've already done that calculation. And then as you kind of get theta closer and closer to 1, you're essentially just going to kind of keep growing. So we know that theta equals 0.6, we get a much higher power of like 0.6 here roughly. And then it'll kind of go up like this and then flatten out. Okay, and so this is going to be your theta in your alternative hypothesis, and then this is your power. And so this is typically kind of how a power curve might look. And so that's the two really important parameters to kind of keep in mind here is that you set the size of your test, and then the power is something you calculate given your acceptance and rejection regions. And you can see that the power will depend on what your alternative hypothesis is. And if your alternative hypothesis is composite, meaning there's more than one theta value in it, you can potentially get you're going to get a power curve for different values of theta. Okay, so that'll be it for today, and we'll go into these concepts in more detail in the next lecture. All right, thank you.